All right, welcome back to the Deep Dive. We're the show where we really try to break down some of the most complex, cutting-edge research. And today, wow, we're looking at a pretty fundamental shift in how AI understands vision and language together.
Yeah, it's definitely a revolution. We're moving past just, bigger models and more data, though that's part of it. We're really digging into the mechanics, the core ideas of how these models align representations.
Starting with CLIP, which was huge, right?
Absolutely. CLIP was the giant leap. But now we're getting into let's say, the finer points, the theory behind stuff like sigmoid contrastive loss and these fascinating geometric structures they call constellations.
Okay, constellations. That sounds intriguing. Let's unpack this. Maybe start with the problem CLIP was trying to solve, the old way of doing computer vision.
Right. So for a long time, the best vision systems, think ImageNet models, they worked with a fixed set of labels, 1,000 categories, maybe a few thousand, whatever the data set defined, that's what the model could see.
And that's inherently limiting, isn't it?
Totally. Because if you, the user, wanted it to recognize something new, I don't know, a specific type of old camera, or maybe a really rare bird, you had to go out, collect tons of new pictures, label them all meticulously.
Which costs time and money.
Exactly. And then retrain the model, or at least a big chunk of it. It just didn't scale to the real world's complexity. It wasn't general.
So the breakthrough idea was learn from language instead.
Precisely. Learn visual stuff directly from natural language supervision. Why? Because text on the internet is, well, it's practically infinite.
All those captions, descriptions, articles.
Billions and billions of image-text pairs just floating out there. It's noisy, it's messy, sure. It's what we call weak supervision. The text isn't always a perfect label.
But the sheer volume makes up for it.
That's the bet. You're tapping into this massive, generalized knowledge base encoded in human language and transferring it to the visual system. It's a completely different paradigm from relying on curated, clean data sets.
And that brings us squarely to CLIP, Contrastive Language Image Pre-Training.
Yep. And CLIP wasn't necessarily the first to try pairing vision and language this way, but it did two things incredibly well: simplification and scale.
Okay, simplify how?
Earlier methods were sometimes more complex. CLIP boiled it down to a really simple, scalable task. You take a batch of images, say N images, and N captions. The model's job is just to figure out which image goes with which caption. A matching game, basically.
Across the whole batch.
Across the whole batch. Is this image paired with caption A, B, C, or D? And this simple proxy task, when done at enormous scale, worked incredibly well.
And the scale.
Yeah.
Let's talk about that 400 million pairs data set.
Yeah, that was custom built, scraped from the internet. It dwarfed previous efforts. You had researchers talking about training weak supervision models for maybe accelerator days.
Right.
CLIP was trained for the equivalent of accelerator years. Massive compute clusters running for weeks. They just blew the scale gap wide open.
And this contrastive approach, matching images and text, meant they learned these powerful general image features without ever needing those clean ImageNet labels during the pre-training phase.
Exactly. And that scale, combined with the language grounding, is what led to these surprising abilities popping up.
Like OCR, reading text and images.
Yeah, OCR, figuring out where things are located, even recognizing actions in videos. Stuff the model wasn't explicitly told to learn. It just absorbed it from the patterns in the data. Language is just that rich a signal.
Okay, so CLIP proves scale and language work. But then the focus shifts, right, to the math, the loss function.
That's the next frontier. CLIP used something called the info-NC loss. It's a standard contrastive loss, relies on a softmax across the batch.
Making the right pair stand out from all the wrong pairs in that specific batch.
Right. It's competitive within the batch.
Yeah.
And it works, obviously, but it's not maybe the most theoretically clean or efficient way. Subsequent work, like SigLIP and SigLIP2 from Google DeepMind, they zeroed in on this. They introduced the sigmoid contrastive loss.
And that's the core of our deep dive today. This shift from the batch softmax info-NC to this pairwise sigmoid loss.
Exactly. It's not just a minor tweak. It led to better theoretical grounding, better efficiency, and this whole fascinating geometric picture involving these constellations.
All right. So first, let's make sure we fully understand CLIP, the architecture, how it works, especially that zero-shot magic. Then we'll tackle the theory, and finally, get into SigLIP and those constellations. Sound good?
Sound like a plan. Okay, part one. Before CLIP really nailed the contrastive approach, there were earlier attempts. You mentioned Vertex, some early CLIP prototypes. They actually tried something harder first. a predictive objective.
Meaning?
Meaning they tried to train the image model and the text model together to predict the actual words in the caption for a given image.
Wow, okay, that sounds way harder than just matching, like generating the text.
Exactly, generating the text or predicting a bag of words representation of it. And you can imagine web captions are all over the place.
Oh yeah, descriptive, sarcastic, just random keywords.
Precisely. Trying to predict that variety. It turned out to be incredibly inefficient computationally. The sources point out, for instance, a 63 million parameter language model they used in early tests. It took twice the compute of the image encoder, the ResNet 50,
Okay.
but it learned ImageNet concepts 3 times slower than a much simpler baseline. It was just bogged down trying to master language generation instead of the core visual concepts.
So predicting the exact text was a dead end, computationally speaking.
Pretty much. So they pivoted from predictive to contrastive.
The matching game. Just predict if this text goes with this image, yes or no, compared to other texts in the batch.
And that shift was the breakthrough. The sources say it gave them a 4x efficiency improvement in how quickly the model learned to do zero-shot classification on ImageNet compared to the predictive baseline.
4 times faster just by changing the objective.
Yeah, it showed the goal wasn't perfect language mimicry. It was about finding that shared space, that embedding space where related image and text concepts could, find each other, cluster together.
Okay, so let's look at the architecture that did this. 2 towers, right? One for images, one for text.
Right. Separate encoders, optimized for their own modality. For images, they tried both ResNets, scaling them up ridiculously, like the RN50x64 version, and also vision transformers, VITs. The VIT-L14, especially when fine-tuned at a higher resolution like 336 pixels, seemed to work best eventually.
And for text.
A standard transformer architecture. But crucially, it's designed to output just one fixed-length vector, one embedding, representing the whole meaning of the text snippet, not predicting word by word.
Got it. And the training, you mentioned the scale before. Any specifics on the hyperparameters? They sound intense.
Oh, they are. The mini batch size was 32,768.
32,000.
Yep. Compare that to like 32 or 64 in a typical academic paper. It's enormous. They trained for 32 epochs using the Atom Optimizer, mixed precision to save memory. They even used gradient checkpointing, which trades compute for memory, just to make these huge models fit and train stably.
That's serious engineering. What was the compute cost?
The best VIT model, the L14, took 12 days on 256 V100 GPUs. The biggest ResNet monster, the RN50x64, needed 18 days on almost 600 V100s.
Wow. So not something you whip up in your garage. This was a massive, deliberate push on scale.
Absolutely, a brute force effort to see just how far this language supervision idea could go.
Okay, so they trained this giant model to match images and text. Now the payoff, zero-shot transfer. How does that actually work? It feels like magic.
It does feel a bit like matching, but it's actually quite elegant. Remember, the model is trained for retrieval, matching. To do classification, say on ImageNet, you don't retrain anything. You just repurpose that retrieval skill.
How?
You take your class names, cat, dog, airplane, car, whatever, and you turn them into text prompts. Often something like a photo of a cat, a photo of a dog.
Okay, treating the labels as text queries.
Exactly. Then you feed your input image through the image encoder to get its embedding vector. And you feed all your text prompts like a photo of a cat, a photo of a dog, etc., through the text encoder to get their embedding vectors.
So now you have one image vector and, say, 1,000 text vectors in the same space.
Precisely. Since they're in the same shared space, you can measure how similar they are. The standard way is cosine similarity, basically, the angle between the vectors. Closer angle means more similar concepts.
Makes sense.
You calculate the cosine similarity between the image vector and each of the text vectors. Then you apply a learned temperature scaling factor, tau.
Temperature, like in softmax.
Exactly like in softmax. It sharpens or softens the distribution. Then you pass those scaled similarities through a softmax function.
And that gives you a probability distribution over the classes.
Bingo. The class whose text prompt embedding is most similar to the image embedding gets the highest probability.
That is clever. So the model isn't learning cat from labeled cat pictures. It's learning cat because the vector for the image is closest to the vector generated from the text, a photo of a cat.
You got it. And the really cool interpretation here is that this whole zero-shot mechanism, it's mathematically equivalent to a standard linear classifier like logistic regression. Think about a normal classifier. You have input features from the image encoder and learned weights for each class. The weights determine the decision boundary. In zero-shot SigLIP, the text encoder acts like a dynamic weight generator. It takes the class name text, a photo of a cat, and generates the weight vector for that class on the fly.
Whoa, so instead of learning weights from a million labeled images?
You generate the weights directly from the language description of the class. It's like the text encoder is a hypernetwork creating the classifier.
Yeah, that's really elegant. It bypasses the need for massive labeled data sets for new classification tasks.
It's the power of leveraging language. It provides this incredible free source of supervision that connects visual patterns to semantic meaning.
And the results. How well did this zero-shot approach actually perform?
Astonishingly well, especially at the time. Zero-shot SigLIP, again, without seeing any of the 1.28 million ImageNet training examples, matched the accuracy of the original ResNet 50 model that was fully supervised on ImageNet.
That's a huge milestone, beating the supervised incumbent without supervision.
Well, matching it, but yeah, a massive proof of concept. And it got even better when they looked beyond just ImageNet. They tested it on a suite of 27 diverse datasets, OCR, action recognition, fine-grained classification, all sorts of stuff. Yeah. On 16 out of those 27 datasets, zero-shot SigLIP actually outperformed a fully supervised linear classifier trained on top of ResNet 50 features.
Outperformed supervised methods in many cases.
Especially in areas where ImageNet's focus on static objects wasn't enough, like action recognition. On the Kinetics 700 dataset, zero-shot SigLIP was 14.5% better than the supervised ResNet 50 baseline.
Why such a big jump there?
Because action recognition involves verbs, scenes, context, things that are naturally described in language captions, but maybe less directly captured by ImageNet's noun-centric labels. The language prior was just richer for those kinds of tasks.
That makes sense. What about few-shot learning, where you have maybe just a handful of examples?
Also really interesting results. On average, across datasets, zero-shot SigLIP performed about as well as a logistic regression classifier that was given 4 shots, 4 labeled examples per class, using the same SigLIP image features.
So the language description alone is as good as seeing 4 actual pictures.
Roughly, yeah. It suggests that the language prompt, a photo of a specific bird species, is such a powerful and efficient way to define the concept's boundaries in the feature space that supervised learning needs multiple visual examples just to catch up and infer those same boundaries indirectly. Language gives you a massive head start.
Okay, so SigLIP is incredibly powerful, leverages language, works zero-shot. To understand where things went next with SigLIP, we probably need to touch on some core ideas from representation learning theory itself.
Yeah, definitely. Stepping back a bit helps frame the later innovations. Representation learning, I mean, it's kind of the heart of deep learn, right?
Learning good features from the data.
Exactly. It's about learning transformations of the raw input, the pixels, the text tokens that make it easier to do something useful with it, like classification or generation or whatever your downstream task is. The goal is often described as disentangling the underlying factors of variation in the data, finding the independent knobs, if you like, that explain why the data looks the way it does.
And deep learning models, with all their layers, are good at this.
That's the idea. Deep architectures, stacking layers of nonlinear processing seem to encourage the model to reuse features and build up increasingly abstract representations. Lower layers might detect edges and textures, higher layers might combine those into object parts, and even higher layers might represent whole objects or concepts.
Getting more abstract and hopefully more invariant.
Right. Invariant to irrelevant changes like lighting, viewpoint, background clutter, recognizing the catness regardless of the specifics. That's the classic goal.
And how does this connect to SigLIP's pre-training?
There's a key principle. Representations that are good for modeling the input data itself, PX, understanding the structure of images and text on the web, often turn out to be good for predicting specific targets, PYX.
Like matching images and captions or classifying images.
Exactly. Learning the general structure helps with specific tasks. This lets us share statistical strength. The knowledge gained from billions of unlabeled web pairs helps the model perform well on a specific benchmark, even with 0 or few labels for that benchmark. It's the foundation of semi-supervised learning and transfer learning.
Okay, so CP is learning these shared representations. Now, let's talk about the geometry. The inferency loss that CPOP used. What was the intended geometric outcome?
Well, the intuition behind InfoNC and similar contrastive losses used in models like ELIG was really about achieving alignment.
Meaning the vector for cat text should ideally be the same or very, very close to the vector for a cat image.
That was the traditional understanding, yeah. The math of the InfoNC loss pushes the similarity, like cosine similarity or dot product, of positive pairs, matching image and text, to be high, while pushing the similarity of negative pairs, mismatched image and text to be low relative to the whole batch.
So you'd expect things to merge in the embedding space. Cat images and cat text should occupy the same spot.
That was the expectation, but that's not what happened when people actually trained these massive models and looked closely at the resulting embeddings.
Ah, the plot thickens. What did they find?
They consistently found something called the modality gap.
Modality gap. Okay, what is that?
It's the empirical finding that even after extensive training with InfoNC, aiming for alignment, the image representations and the text representations ended up in distinct, separate regions of the embedding space.
They didn't merge?
Nope, they were clearly separated. You could, in fact, train a simple linear classifier to perfectly distinguish between image embeddings and text embeddings. They were linearly separable.
Wow. So the model was trained to bring them together, but they ended up apart. That seems counterintuitive.
It was definitely surprising to many. The initial reaction was, maybe it's an artifact. Maybe the different architectures of EIT for images, a transformer for text, inherently can't produce perfectly aligned features.
A reasonable first guess.
But further experiments kind of debunk that. The gap persisted even with more similar architectures. The consensus shifted. The modality gap wasn't a bug or an architectural limitation. It seemed to be an intrinsic consequence of optimizing the InfoNC loss itself, especially at scale.
So the loss function itself encourages separation, even though it aims for high positive similarity. How does that work?
It's tied to the competitive nature of the softmax normalization in InfoNC, to make the one positive pair stand out strongly against all the negative pairs in a large batch. It turns out to be easier for the model to slightly push the entire cluster of image embeddings away from the entire cluster of text embedding.
Creating some distance between the modalities overall.
Exactly. This increases the average distance between modalities, intermodal distance, while still ensuring that within that separated structure, the positive pairs are closer to each other than to negative pairs, intermodal distance. So you achieve synchronization. The cat image vector is closest to the cat text vector, but not alignment. The vectors don't actually overlap. They live in separate neighborhoods.
Synchronization without alignment. That's a key distinction.
A crucial one. Understanding that the optimal solution under InfoNC might actually involve this separation, this modality gap, was a really important insight. It paved the way for thinking differently about the loss function itself.
Okay, so InfoNC leads to this somewhat messy, empirically observed modality gap. The representations synchronize but don't align. This feels like the perfect setup for asking,
Yeah.
can we design a loss function that explicitly accounts for this? Maybe even leverages it?
Precisely. And that's where SigLIP and SigLIP2 come into the picture. Developed primarily by Google DeepMind, their big move was to ditch the batchwise softmax of InfoNC
And replace it with?
a pairwise sigmoid contrastive loss. This is a really fundamental change in perspective.
How so? Pairwise versus batchwise.
With InfoNCE, the score for a positive pair depends on all the negative pairs in that specific batch. It's a relative comparison. With the sigmoid loss used in SigLIP, each pair, whether it's a positive matching pair or a negative mismatch pair, is evaluated independently. Its contribution to the total loss doesn't depend on what other negatives happen to be in the current batch.
Okay, independent evaluation. What else is different?
The other absolutely crucial difference is that the SigLIP loss explicitly includes trainable parameters within the loss calculation itself. A trainable inverse temperature, denoted $2, and a trainable bias, denoted $.
So $2 are learned during training, just like the model weights.
Exactly. And having these learnable parameters completely changes the geometry of the optimal solution, the state where the loss is minimized.
How does it change the geometry?
This leads to the really cool theoretical finding behind SigLIP. The researchers showed that this sigmoid loss with trainable dollar and bad dollars can be driven perfectly to zero, a true global minimum. And this zero loss state isn't achieved by perfect alignment, but by arranging the embeddings into specific geometric configurations they called Iola constellations.
Okay, MB all constellations. This sounds like where the math gets interesting. Let's break that down. What are Dever-Eilbrand?
Think of them as defining the rules for an optimally separated embedding space. IRL is the margin it has to be non-negative. NRL is the relative bias. For a set of embeddings, let's say unit vectors UE for images and $5 for text to form a zero-loss constellation, they have to satisfy two strict conditions based on their inner products, which measure similarity.
Condition 1.
For all the mashing pairs, ILM matched with ILR, their inner product must be greater than or equal to the relative bias plus the margin. Now we redo Nalaral plus Bielabril.
So positive pairs have to be clearly on one side of some boundary with a buffer.
Exactly. And condition 2. For all the non-matching pairs, matched with UI as UAI Fidu, their inner product must be less than or equal to the relative bias minus the margin. Langle, UI, VJ Wrangle plus Burrell.
And negative pairs have to be clearly on the other side of that boundary, again with that same buffer dollars.
Precisely. Burrell defines the center of this separation, and Darrell defines the width of the gap or no man's land that must exist between the similarities of positive pairs and the similarities of negative pairs.
So the existence of some positive margin dollar and a relative bias that satisfy these conditions is basically proof that you've reached the ideal state for this loss function.
It's the necessary and sufficient condition. If you can find a Mortimer-Miller and a Borel that work for all pairs, your configuration is a global minimum for the sigmoid loss with learnable dollar and dollars.
And this directly explains the modality gap.
Perfectly. The constellation formulation provides the theoretical justification for why separation is optimal. The requirement that many-Langle UI V-Wrangle must be strictly greater than maxi-Langle UI VJ-Wrangle by at least 2 millars, in fact, mathematically mandates that the positive and negative similarities are cleanly separated. This allows, and in fact encourages, the image and text representations to live in distinct, linearly separable regions, confirming the empirical observations from SigLIP, but now with a solid theoretical underpinning. Synchronization, structured separation. That's the goal.
Okay, that's theoretically elegant. What about practically? What does that margin buy you in the real world?
The margin dollar is incredibly important for practical applications, especially anything involving retrieval or search. A larger margin dollar means the configuration is more robust to errors.
Errors like what?
Think about searching in these huge embedding spaces. Finding the exact nearest neighbor can be very slow, computationally expensive. So real-world systems often use approximate nearest neighbor ANN search algorithms,
Which are faster but might make small mistakes.
Exactly. If your constellation has a large margin, $2, it means there's a big buffer zone. Even if the ANN search is slightly off, it's much less likely to cross that boundary and retrieve the wrong item. The correct match is just so clearly separated from all the incorrect ones.
So a bigger dollar means more reliable search, even with faster approximate methods.
Yep. It provides robustness against noise and approximation, which is critical for deploying these models efficiently. SigLIP isn't just theoretically cleaner, it's potentially more robust in practice because of this margin concept.
Okay, that makes the shift very compelling. Now, you mentioned the loss has trainable tod in the dollars. How does the training actually find these constellations? Does it just naturally happen?
Well, the researchers noticed something interesting. When using the standard formulation of the sigmoid loss, the optimization process often tended to converge to solutions where the relative bias was close to 0 prox.
Why is that a problem?
It's not necessarily a problem, but it might be artificially limiting the kinds of geometric solutions the model can find. Maybe the truly optimal separation isn't perfectly centered around 0 similarity. So they proposed a slight modification, a reparameterization they called LRB-Sig. The key idea was to make Biddle itself an explicitly trainable parameter, disentangling it slightly from $2 and the original bias dollar.
So you train $2 and Birol directly.
Basically, yes. This gives the optimization more direct control over the center of the separation, as well as the steepness and overall shift.
Did that help?
Experiments on synthetic beta suggested it did. It led to faster convergence to 0 loss, and importantly, it opened up the possibility of exploring a wider range of constellation geometries. You could even, in theory, freeze a biral at a specific non-zero value during training to actively guide the model towards a particular kind of separated structure. That's a neat, low-level design capability.
Do we know what values these parameters take in real models? Like, what did a trained SigLIP model end up learning for $2 in bottle?
Yeah, they reported values for one of their SigLIP2 models, a B16 variant. It learned an inverse temperature around 117.8 does.
Pretty high, so a steep sigmoid function.
Right, and a bias Ballarder around Menical 12.9. When they calculated the resulting relative bias from these, it came out to roughly Menical 0.1.
So definitely not 0. The optimal separation point was slightly shifted.
Exactly. It found a stable, zero-loss constellation that wasn't centered at 0 similarity, demonstrating the value of those trainable parameters in finding the true minimum. The geometry is explicit and optimized.
Okay, let's recap the evolution then. SigLIP2 used info ends, scaled massively, and kind of accidentally discovered the modality gap because that's where InfoSeed tends to lead.
Right, more observational.
Yeah, and SigLIP comes along, replaces the info ends with the pairwise sigmoid loss, adds trainable tolls and dollars. It gets this beautiful theoretical framework of combinatorial constellations that guarantees zero loss and justifies the separation, giving robustness via the margin dollars.
Much more deliberate geometric engineering.
And SigLIP2. Is that another leap in loss function?
Not fundamentally in the core loss. SigLIP2 builds on the same sigmoid loss and constellation idea, but refines the training recipe. It adds things like auxiliary decoders during training and uses self-distillation techniques. These are more about improving training efficiency, stability, and squeezing out even more performance, especially as you scale up to larger models. It makes the whole SigLIP approach even more practical and performant.
Got it. So SigLIP, SigLIP2 represent a shift from brute force scale finding an implicit structure to theoretically grounded optimization, explicitly creating a desired geometric structure.
That's a great way to summarize it, from observation to deliberate design based on the geometry of the loss landscape.
This theoretical elegance of constellations in the sigmoid loss is nice, but does it actually translate into real-world advantages? You mentioned efficiency and robustness.
Oh, absolutely. Big time. Let's start with efficiency, because that's often crucial for getting models deployed, especially outside of giant tech labs. Remember how InfoNest needs that softmax across the whole batch?
Right, comparing the positive pair against thousands of negatives?
That's computationally expensive, especially the communication needed between GPUs when you have a massive batch size like 32,000 spread across many chips. Everyone needs to know about everyone else's scores.
Lots of data shuffling.
Exactly. But the pairwise sigmoid loss in SigLIP, it's computed independently for each pair.
So no need for that big batch-wide comparison.
Nope. The calculation is local. This drastically reduces the communication overhead and can significantly speed up the training process, particularly on large distributed systems. It's just inherently more parallelizable and less communication bound.
And we see this play out in practice.
Definitely. There's a great example in the sources involving the clear vision framework. This is about classifying images from traffic cameras, dealing with different weather conditions, lighting, etc. These systems need to be efficient.
Real-time, often on-edge devices.
Right. So they compared adapting a big, powerful CLE-based model, EVA-002, which uses CLP principles, versus using a Vision SigLIP2 approach.
What are the difference?
Huge. For adapting to the traffic camera domain, the EVA-02 model took about 6 hours of training time.
Okay.
The Vision SigLIP2 model. Leveraging the efficiency of that pairwise loss, it took only 30 minutes.
Wow. 6 hours down to 40 minutes.
Yeah, that's like an 89% reduction in training time. Think about how much faster you can iterate, experiment, or deploy updates. It's a massive practical win, especially if you don't have unlimited compute budgets.
And what about inference? The time it takes to actually classify an image once trained.
Equally important for real-time systems. The EVA-02 model took around 15 seconds per inference.
Which is probably too slow for live traffic monitoring.
Way too slow. Conditions change in seconds. The Vision SigLIP2 method, again benefiting from its architecture and potentially the robust separation, got inference down to just 3 seconds.
15 seconds down to 3, an 80% reduction.
Yep. That starts to make real-time, robust classification feasible, even on potentially constrained hardware in, say, a traffic camera pole. Efficiency matters hugely for deployment.
Okay, so major efficiency gains from SigLIP. What about robustness? How do these models handle the messiness of the real world, like distribution shifts?
This is where SigLIP's original strength really shines, and the principles carry over. Because SigLIP was trained on that incredibly diverse, noisy web data.
Not just clean ImageNet pictures.
Right. Pictures in fog, rain, weird angles, bad lighting, artistic renderings, everything. Its learned features were inherently more robust to shifts away from the standard benchmarks compared to models trained only on ImageNet.
How much more robust?
The original SigLIP paper reported that zero-shot SigLIP reduced the gap between its ImageNet accuracy and its accuracy on various distribution shift datasets by up to 75%.
Closing the generalization gap significantly.
Hugely. It actually set new state-of-the-art results on several challenging distribution shift benchmarks at the time, like ImageNet R, renditions, art, ObjectNet, objects in unusual contexts, ImageNet Sketch, and even video datasets like ImageNet Vid and YouTube BB.
So the language grounding helped it generalize better to visual styles and contexts it hadn't seen in curated training sets.
It seems so. The connection to broader concepts via language made the visual features less brittle, less likely to break when the input distribution changed.
And the zero-shot capability helped here too, right? You could tailor the prompts.
Exactly. For datasets like the video ones, the classes may be broader superclasses not found in ImageNet. With CLIP, you could just create text prompts for those specific classes, person riding a bike, vehicle driving, and get good performance without retraining. This flexibility boosted robustness further by about 5% on average for those kinds of datasets.
There was also an interesting finding about adapting CLIP features, wasn't there? Like fine-tuning?
Yeah, that was subtle but important. If you took the pre-trained CLIP features and trained a simple linear classifier on top using ImageNet labels, fine-tuning just the head, you could boost the ImageNet accuracy significantly by over 9%.
Sounds good. More accuracy on the benchmark.
But that adaptation actually hurt performance on the distribution shift datasets. The average accuracy on those decreased slightly.
Ah. So specializing for ImageNet made it less robust to the real world.
It seems so. Overfitting to the benchmark distribution, even just a little bit, sacrificed some of that hard-won zero-shot generalization. It highlights a key trade-off, maximizing benchmark scores versus maintaining broad, real-world robustness. The pure zero-shot model was often the most robust overall.
How did CLP compare to other representation learning methods popular around the same time, like SimCLR or MoCo?
Competitively, especially when you looked beyond just ImageNet. On that broader suite of 27 datasets, CLIP often performed better. SimCLR, MoCo, BYOL, those were powerful self-supervised methods, but they were typically trained and benchmarked primarily on visual data like ImageNet. They didn't have the explicit language grounding.
So CLIP's advantage came from language, giving it broader conceptual knowledge.
That seems to be the case. For tasks that relied more heavily on that conceptual understanding, like OCR or geolocalization, CLIP tended to have an edge. Language brought something extra to the table.
Which brings us back to that few-shot comparison point. Zero-shot CLIP matching a four-shot supervised classifier.
Right, it just hammers home how much information is packed into that natural language prompt. Giving the model the text, a photo of a Siberian husky, is like giving it a mini lecture on huskies, their appearance, context, everything. Supervised learning has to painstakingly infer all that from just a few pixel examples. It's just way less efficient. Language provides an incredibly dense, powerful prior.
So it feels like the journey went. CLIP proved language supervision plus scale works wonders for generalization and zero-shot. SIG then refined the underlying math, proving that the optimal structure involves robust geometric separation, synchronization, not alignment, which also brings efficiency benefits.
That sums it up nicely. CLIP cracked the door open with scale, and SigLIP provided the precise geometric key to unlock it more efficiently and robustly. Synchronization underpinned by the mathematics of constellations.
So we've covered a lot of ground today. We traced this path from the sort of brute force scaling of CLIP, dealing with the limitations of the info and C loss, all the way to the mathematical precision of SigLIP's sigmoid contrastive loss and these resulting geometric constellations.
Yeah, it's a fascinating evolution. I think the big takeaway, for me at least, is how much leverage you can get from really understanding and optimizing the geometry of the loss function itself. It's not just about more data or bigger models. Innovations in the core mathematics can unlock huge gains in efficiency and robustness.
It really reframes the modality gap, doesn't it? From being this weird artifact of info and C to being a desirable, optimizable feature of a well-structured representation space, as defined by the constellations.
Exactly. It tells us that maybe the goal shouldn't have been perfect alignment or merging in the first place. High-performing, robust representations seem to require this structured separation, this synchronization across distinct spaces.
Which leads to a pretty provocative thought for the future, doesn't it? If even the mathematically optimal zero-loss state for just two modalities, vision and text, requires them to maintain this separation, this constellation structure, what does that imply when we start thinking about building truly general AI that needs to synchronize many more modalities, like audio, maybe thermal data, 3D scans, touch feedback?
Right. If you need a margin, a separation between images and text, what kind of geometric structure do you need to optimally synchronize sound, vision, and maybe tactile information?
What information must remain distinct in its own modality space, even if it's perfectly correlated with information in another space?
Yeah, think about seeing a bird and hearing it chirp. The visual representation and the audio representation need to be synchronized, obviously. But the constellation idea suggests they also need to remain geometrically separate for the system to work optimally.
So what unique features does the audio embedding need to hold on to? What about the visual one?
Yeah.
What information is fundamentally modality specific, even when describing the same event?
It suggests that maybe the architecture of truly generalized AI isn't going to be one single giant unified embedding space where everything merges.
But maybe more like a complex constellation of constellations, a system of interconnected yet distinct modality spaces, each contributing its unique perspective, optimally separated but precisely synchronized with the others.
That could be. Figuring out the necessary complexity of that geometry, the required independence, and the optimal synchronization between potentially dozens of modalities, that feels like a huge design challenge for the next wave of AI research, understanding the structure of knowledge itself.
A very compelling place to leave it. It's not about merging everything, but about structuring the separation. Thank you for joining us for this deep dive. We hope this gave you a clearer picture of where this exciting field is heading.